We are in Unit 5. This is our fourth section of Unit 5. We've done quite a bit so far, and we've got a huge concept coming up today, and it is the fundamental theorem of calculus. Perhaps the most important thing that we do all year long, fundamental theorem of calculus. This is split up into two parts. So today we're going to do part 1. Okay, let's begin with kind of reviewing a little bit of what we've done so far in Unit 5. So far, just in Unit 5, okay, what we've talked about are two different types of integrals. We've talked about the definite integral, and a definite integral has boundaries. Okay, and we know that a definite integral is the area under the curve from x equals a to x equals b. We know that it's definitely the area, okay? And because it's the area, when we evaluate a definite integral, we get a number. So we get a number. A definite integral is a number because it's the area, right? If we wanted to give that number units, the units would be whatever the y units are multiplied by whatever our x units are. Okay, so if both x and y were in, let's say, centimeters, then the area would be in square centimeters, right? Square centimeters. Now, if x or y was some other unit, then our area's units, our number's units, would be whatever the y is times whatever the x is, right? So in this case, it would be square centimeters, but it could be other things. All right, so it has units. And the name of this, again, is called the definite integral. Okay, so that was our first type of integral. Well, it wasn't our first. We actually did an indefinite integral first. So next comes the indefinite integral. So an indefinite integral does not have boundaries. Okay, and what is this? Well, this is an antiderivative. It's an antiderivative. So this, when we evaluate this, we get not a number, but we get a function. In fact, we get a family of functions because we always put plus c at the end, right? So we get a function whose derivative is f of x, right? And if you put plus c on the end, we get all of the functions whose derivatives are f of x. Okay, functions here. Okay, so it's a family of functions as opposed to a number up here, right? Okay, and it's called an indefinite integral. Okay, so that's the comparison of the two things that we have studied so far in Unit 5. All right, in this section, the fundamental theorem of calculus, what it does is it ties these two together. These, if you just looked at the description, you would think that these are two extremely different things, right? Now, if you look at this, obviously they look very similar to each other, right? But if you ignore that and only look at the descriptions, they appear to be very different. The fundamental theorem of calculus gives us a relationship between these two, okay? All right. So let's recall something about an indefinite integral. Let's look at this indefinite integral. Let's say we have the antiderivative of 12x cubed dx. Okay, let's recall what we did with that. We raised the power by 1, right? Raise the power by 1 because we're doing the opposite of a derivative. Okay, raise the power by 1 and then divide this coefficient by our new power. So 12 divided by 4 would be 3, right? And then we add any constant. So this is called the constant of integration. If you take the derivative of this, you get back your 12x cubed, right? So the derivative of 3x to the 4th plus c gives us back our 12x cubed, okay? So for our purposes today, what we're going to do is we're going to call this piece f of x, okay? And I want to call this piece something as well, all right? And since it's related to f of x, I don't really want to call it g of x or h of x or something. I want to call it something that relates to f of x. So I'm going to call it, and this is like generally done, it's accepted notation here. This we're going to call capital F of x. Capital F of x. Okay, so from here on out, you guys, when you write a lowercase letter, that is different. It's a different function from the same letter, but in another case, in an uppercase. Okay, so be careful with your writing. Be careful. So we are saying that the derivative of capital F of x is equal to lowercase f of x. All right? So f of x, capital F of x, is an antiderivative of lowercase f of x. Okay? All right. So this is how we relate the definite integral with an indefinite integral. So then we can say that the integral from, let's just give it some boundaries, 2 to 4, and I want to use the same f of x. I want to use 12x cubed dx. What we will do here is we will find the antiderivative. So we're going to find capital F of x. We know that that's 3x to the 4th. And we evaluate that. We evaluate that at our upper boundary. So I'm going to say at x equals 4. And then we subtract the same antiderivative evaluated at our lower boundary. Okay? That's how they are related. So this would be 3 times 4 to the 4th minus 3 times 2 to the 4th. And that would be our definite integral. Okay? If where is my calculator? If I want to just prove this to you, that this will work out. Not prove, I'm not giving any rigorous mathematical proof here. I'm just showing you that in this particular instance, it works out. So if we did this 3 times 4 to the 4th minus 3 times 2 to the 4th, we get 720, right? 720. And then if we do our math 9 on this, math 9, from 2 to 4 of 12x cubed dx, we get 720. All right? So this is the way that the indefinite integral relates to the definite integral. Okay? So we can write this another way using instead of using the 12x cubed and the 3x to the 4th, we can say, so the way we're going to write this is I could write a to b here. Let me just write a to b. The integral from a to b of any function is its antiderivative. Remember we called this capital F? So its antiderivative evaluated at the upper boundary minus the antiderivative evaluated at the lower boundary. And that is the fundamental theorem of calculus, part 1. So let's write that out. It's huge. Fundamental theorem of calculus, part 1. We're going to have a part 2 tomorrow. Okay? Fundamental theorem of calculus, part 1. Okay, is if f of x is continuous on some closed interval a to b, and capital F of x is an antiderivative of f of x on a to b, then the integral from a to b of f of x dx is equal to the antiderivative at b minus the antiderivative at a. Huge. We will use this the entire rest of the year. Okay? There are different ways we can use it as well. Okay. I told you that I showed you like an example of when it works, but I didn't prove this theorem. If you want to see a proof of this, I posted on our Schoology. On our Schoology, I posted a video proof that I found online that is nice. I could go through that myself, but it does take a little time to do it. So I thought I'd just leave it on there for you if you want to see it. Okay. All right. Let's look at some examples. Okay. Let's look at some examples. So example 1. Let's say that we have the integral from 0 to 1 of 2x minus 1 squared dx. Okay. If we were to graph this, it would give us a parabola, right? And we don't have a geometric formula to give us the area under a parabola, right? So what we did last time with finding, evaluating definite integrals, just drawing a picture and using the area of a rectangle or area of a triangle or area of a circle, that's fine for those, but in general we can't do that, right? So the first and hardest step in any integral is finding the antiderivative. So you have to look at this and say, how can I find the antiderivative? Okay. Well, all we know is the power rule and our antiderivatives of our trig functions. Right now, that's all we know. So we have to be able to use the power rule. And right now, this is not in a form where we can use the power rule. So I need to actually multiply out this binomial. So I need to square this binomial. When I square this binomial, I'll have 4x squared minus 4x, double the product, right? Plus 1, the square of negative 1, dx. Now I can apply the power rule. Okay, pay attention to my notation here, all right? I'm applying the power rule, so I'm going to get x cubed and then 4 over 3, right? Raise the power. Looks a little bit fuzzy here. Raise the power by 1 and then divide the coefficient by the new power, right? Minus x squared, and then 4 over 2 is 2. And then the antiderivative of 1 is x. Now usually we would put a plus c. In a definite integral, you don't have to. If you really want to, you can. It'll end up subtracting itself out, all right? So in a definite integral, we don't need the plus c. Now, here comes the notation. we're going to evaluate this from 0 to 1. This is the notation for that. We're evaluating the entire antiderivative from 0 to 1. So these boundaries, move those boundaries over here in this step. Okay? Now we begin by plugging in the top boundary. Always do the top first. That's our B, right? That's our f of B, which in the fundamental theorem, that is the positive. Where's it at here? Goodness, let me grab this. F of B comes first. B is on top. So always do that top boundary first. Okay? All right, so this will be 4/3 times 1 cubed minus 2 times 1 squared plus 1. That's the antiderivative at 1. And then we subtract the antiderivative at 0. So now we're plugging 0 in for x. Well, we see that everything has a 0 here, so that's not going to be, that's not going to affect our answer here. And then this would be a safe stop spot, but these will be multiple choice questions, you guys. So get used to doing a little bit without a calculator. Okay, this would be 4/3 minus 2 plus 1, so 4/3 minus 1, and 4/3 minus 3/3 is 1/3. Okay. Number 2. Let's say that we have the integral from 1 to 4 of u minus 2, I'm changing the variable from x to u minus 2 over the square root of u du. Okay, so the first step is always the hardest one. It's how do we make this something that we can use the power rule on? Okay, we have to find the antiderivative, and so how do we do that? Well, and this just takes practice, you guys, knowing what to do. What I see is I see a single thing in the denominator, and if I see a single thing in the denominator, this is what I want to do. Split up my numerator. You can split up your numerator. You cannot so easily split up a denominator, but you can split up that numerator. So u over u to the 1/2. U divided by u to the 1/2 is u to the 1/2. Subtract your powers. Minus 2 divided by u to the 1/2 is 2u to the negative 1/2. We have to make this something that we can use the power rule on. So it has to be your variable to a power. Variable to a power. Has to be. Not having the variable to the power in a denominator. It has to be up on top. Okay? Now we can use the power rule. So the power rule says add 1 to the exponent. If we add 1 to 1/2, we get 3/2. And then we multiply by 1 divided by 3/2, which is 2/3. Okay? Our next variable here, u to the add 1 to negative 1/2, and we get positive 1/2. And then we're multiplying this negative 2 times, we're dividing negative 2 by 1/2, which is the same thing as multiplying that negative 2 times 2. So we get negative 4. Okay? And then we evaluate this from 1 to 4. Okay? Now, if this was free response, and it won't be, but if this was free response, all we would have to do is put the 4 in, and then subtract and put the 1 in. This is a safe stop spot. But like I said, these will be multiple choice. So you are going to have to evaluate, you're going to have to know how to handle these things. So this 2 in the bottom means square root. So the square root of 4 is 2, and then 2 cubed is 8. So this is 2/3 times 8, or 16/3. the square root of 4 is 2. 2 to the first is 2. 2 times negative 4 is negative 8. Right? And then over here we just have minus 2/3 plus 4. So this will be 16/3 minus 2/3 is 14/3 minus 4. 4 is 12/3, and 14/3 minus 12/3 is 2/3. So the multiple choice answer would be right here. Okay? And these will be without a calculator, so you are going to need to do things like that. Okay? But if you practice, you'll be fine. Okay, next up. The integral from 0 to 3. We love to have zeros as boundaries because they're very easy. Usually they're easy to plug in, right? We like zeros and we like ones in boundaries. Okay, this time we have an absolute value function. Let's see what we do for this absolute value function. And before we do, let's get an idea of what's happening here. Okay, whenever you see an absolute value in a function, I want you to go off to the side and sketch that little graph to see what's happening. Okay? Let's go off to the side and sketch this. First, sketch it with no absolute values, and then that will help you sketch it with the absolute values. Well, without the absolute values, this is a parabola pointing up, shifted down 4 units. What's this x value right here? And what's this x value right here? It would be the x value that makes y 0, so that needs to be a 2 and a negative 2, right? So that's this graph. So what does the absolute value do? It makes anything that was negative positive. It flips it over the x-axis. So the parabola will start off looking exactly the same, but then for this piece it'll flip over, and then it'll finish the same way, right? So this is negative 2 and this is 2. Now for us, we want the integral from 0 to 3. So we're only interested from 0, get another color here, from 0 to 3. So we want this area. So think about how you can get that. It did look like this, right? You see that this area and this area stay the same, right? So we can keep that piece. The other one, how are they related? The areas are the same, but the integral of this piece would be negative, and the integral of this piece needs to be positive, right? So we're going to split this integral. So we're going to split this integral up into 2 pieces. One piece is going to go from 0 to 2, and one piece is going to go from 2 to 3. The piece that's 2 to 3 is the same with or without the absolute values, isn't it? So I'm just going to keep that, x squared minus 4 dx. They're exactly the same. This piece, though, I need it to be the opposite, right? I need to be the opposite. So there are 2 ways to do that. I can either put the negative outside the integral, or I can put a negative inside the integral. Either way is fine. I like to put it outside the integral. Okay? So then, if I do that, I will get the value that I want. Okay? It'll be the opposite of this negative area. That'll give us this positive area here. Okay? Alright, antiderivative time. Fortunately, these are both already in the form where we can use the power rule, and they are the same, so what we get for one, we'll get for the other one. So I'm bringing down this negative, and then I'll have x cubed times 1/3 minus 4x evaluated from 0 to 2 plus the same thing, 1/3 x cubed minus 4x, this time evaluated from 2 to 3. Okay? So now it's plug-in time. Well, when we plug the 2 in for x, we're going to get 8/3 minus 8. When you plug the 0 in for x, we just get 0. When we plug 3 in for x, we have x cubed over 3, which is just x squared, or we have 3 cubed over 3, which is just 3 squared, or 9, minus 12. And then remember, you always subtract what you get when you put the 2 in, the bottom boundary in. So this will be 8/3 minus 8. This would be the safe stop spot, but again, these will be multiple choice questions, so you are going to need to simplify this. So let's see what we get. We have a negative 8/3 plus 8, and then we have 9 minus 12, that's a negative 3, and then minus 8/3 plus 8. Right? So this is 16 minus 3, and that's 13, and then minus negative 8/3 minus 8/3 is negative 16/3, right? 13 is 39/3, and 39/3 minus 16/3 would be 23/3. That would be your MC answer. Okay? If you are finding a definite integral of an absolute value, you will always get a positive answer because the entire curve is above the x-axis. So you'll always get a positive answer. All right, next example. Example 4. Oh, by the way, you can always check your answers if you have a calculator, right? Here we want the definite integral, so math 9, okay, 0 to 3. The absolute value function, the easiest place I know to find absolute value, I believe it's right here in F2. So if we do the green alpha and then F2, the very first one there is absolute value. This is also another place to get the derivative and integral, but math 8 and 9 also work for that. All right, so 1 for absolute value, and then there you see the absolute value symbol. So x squared minus 4 dx. And we should get 23/3. And again, I already can see that there's this error that came from the numerical way that this calculator evaluates a definite integral. Okay, so this would be an error. So if I do 23/3, you see they're close, but there's definitely an error in the numerical method that the calculator used, that algorithm. Okay. All right. Very good. Okay, example 4. Let's say that we have the integral from, let's go from negative pi over 6 to pi over 6, and let's put secant squared x dx. Okay, definitely one we cannot use the power rule on, right? We have to think to ourselves, what function's derivative is secant squared x? So what is the antiderivative of secant squared x? Well, the function whose derivative is secant squared is tangent x, right? So our antiderivative is tangent x, not tangent squared, because the derivative of tangent x is secant squared x. Okay? And we need to evaluate tangent x from negative pi over 6 to pi over 6. That will give us tangent pi over 6 minus tangent negative pi over 6. And if this was a free response question, that would be a safe stop spot. Anything that you can put into a scientific calculator is a safe stop spot. Not graphing calculator, scientific calculator. And scientific calculators do have all the trig functions. Okay? All right, but if this is a no calculator, and if it is a multiple choice, which it likely will be, we would need to be able to do this on our own. So tangent of pi over 6 is square root of 3 over 3. Tangent of negative pi over 6, remember the graph of tangent looks like that, right? So if tangent of pi over 6 is square root of 3 over 3, tangent of negative pi over 6 is going to be negative square root of 3 over 3. So this is 2 square root of 3 over 3. Okay? Secant squared is always positive. It's something squared, right? Secant squared is always positive. So it makes sense that our answer would be positive because the curve secant squared is always above the x-axis. So the area underneath it will be positive. Okay, number 5. Let's do another trig. 0 to pi over 4 secant squared theta divided by 1 plus tangent squared theta. Okay, remember, the only thing we know now when we see a trig function, later on it'll be a little bit more complicated, but right now we have to have this be something that we know the antiderivative of. Not piece by piece, but the entire thing, okay? This is a single term, so we have to know a function whose antiderivative is that. And if we don't, then we need to use a trig identity or two until we get something that, like this, we knew the antiderivative of. Okay? So we certainly I don't know a function whose derivative is secant squared theta over 1 plus tangent squared theta, right? So we need to think about a trig identity to use. In the denominator here, I see 1 plus tangent squared theta, and that makes me think of the Pythagorean identities. Sine squared plus cosine squared is 1. If we want tangent squared, so I'm going to divide both sides by by cosine squared, and that will give me sine over cosine or tangent squared. So this would be sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. 1 over cosine squared is secant squared. Okay? So this denominator is the same as secant squared theta. What can we do with secant squared theta over secant squared theta? Well, that reduces to 1. Once I have just a number, then I remember that one property that we had, if it's just a constant here. If it's just a constant, then it's that constant times b minus a. Do you remember that property? So this integral turns out to be just pi over 4. We could check that on our calculator. Okay? You can always check any definite integral using your calculator. Okay, number 6, just a couple more of these. 2t plus cosine t dt. Okay. So do we know an antiderivative of 2t? Sure, we can use the power rule for that. Do we know an antiderivative of cosine t? Do we know a function whose derivative is cosine t? Sure, sine t, right? So we know the antiderivatives of both pieces here. So this would be t squared times 2 over 2, which is 1. And then the antiderivative of cosine t is sine t. You can always check this. Take the derivative. See if you get this back. Now we're going to evaluate this from negative pi over 2 to pi over 2. So first plug in pi over 2. If you plug in pi over 2 in for t, you're going to get pi squared over 2 squared. If I plug in pi over 2 here, sine of pi over 2 is 1 minus. Now plug in negative pi over 2. We're going to get pi squared over 2 squared again, plus sine of negative pi over 2. The graph of sine looks like this. Okay, so sine of negative pi over 2 will be a negative 1. So we have pi squared over 4 minus pi, well, let me write that out. Pi squared over 4 plus 1 minus pi squared over 4 plus 1. The pi squared over 4s, they cancel out, and we're left with just 2. So this is just 2. Okay, again, check it on your calculator. Plug it in. Get practice doing that. Number 7. Integral 1 to 8 of the square root of 2 over x dx. How can we write this as some coefficient times x to some power? Remember, that's what you want to have happen. That's the only way we can use the power rule. I want to write this as some coefficient times x to some power. So I'm going to begin by breaking this up into square root of 2 over square root of x. That's kind of the key there to see what needs to be done. So then we have square root of 2 times x to the what? X to the negative 1/2. Everything that you've done before this course, we pull back out, and you're expected to know what to do with it. Okay, whether it's trig or exponent, dealing with exponents, we do this all the time. Okay. All right. So time for antiderivative. Start with your x to the power. So our new power will be positive 1/2 because we add 1 to negative 1/2. Now I'm going to be multiplying my coefficient times 2 because that's the reciprocal of 1/2, right? So this will be 2 square root of 2. And then we evaluate that from 1 to 8. So I'm going to have first put 8 in for x. So I'll have 2 square root of 2 times square root of 8, right? Minus 2 square root of 2 times 1. This is the square root of 16, which is 4. 2 times 4 is 8. So the multiple choice answer would be right here. Okay? All right. So those were some examples of just using the fundamental theorem of calculus. Let's see what else the fundamental theorem of calculus does for us. Okay, so let's think about this first part of the fundamental theorem of calculus. By the way, we abbreviate fundamental theorem of calculus as FToC, fundamental theorem of calculus. And part 1 says that the integral from a to b of a function is the antiderivative evaluated at b, the top boundary, minus the antiderivative evaluated at a, the bottom boundary. And that is if f prime, capital F prime, is equal to, so if the derivative of capital F is f, right? Now, I want to write this on the left and write this on the right. Okay, so now I'm going to write this as the antiderivative at b minus the antiderivative of f is the integral from a to b of f of x dx. Now, in place of f of x dx, I can write f prime because they're equal. F is equal to f prime, so I'm going to write that as f prime because it is equal, right? So I have, so I have this. Antiderivative of b, or f at b minus f at a equals the integral a to b of f prime of x dx. Okay? So whatever functions are here, the derivative has to be there. It's what we've been doing all along here today, so far. Okay? Now there's nothing magical about capital F. I could change capital F to anything I wanted. Maybe I'll change it to B. I'm sorry, to G. So if I have G out here, this has got to be what? It has got to be G prime. If I have H out here, then what function needs to be in the integral? H prime has to be. We might have T's or U's or some other variable, but if H is the function out here, this has got to be H prime. Okay? So I could even change it to lowercase f. Okay? So, and this is, we usually use lowercase f as our kind of general case scenario. So think about what this is. This is the function evaluated at b. That's a y value. And this is another function evaluated at a, another y value. So this is a y value. So if we have a curve, this would be like f of b, and this would be like f of a, right? The function at b minus the function at a is always equal to this definite integral. Okay? All right, another way to say this is the change in f from a to b. Okay? So this is another way to write the first fundamental theorem of calculus. I'm sorry, the fundamental theorem of calculus, part 1. Some books call it the first fundamental theorem of calculus. I like to think of it as there's only one, we just have two parts. So this is part 1 of the fundamental theorem of calculus. So this is another way to think of it. Okay? Let's look at an example. Let's say that we have, if f prime of x is 5x to the 4th plus 10x, and f of 1 is 3, find f of 2. All right. So what this version of the fundamental theorem of calculus says is if we know a point, we can find any other point we want as long as we have the derivative of that function. Let's set up the first fundamental theorem. Okay, 2 is bigger than 1. So in my integral, 2 needs to go on top, 1 needs to go on the bottom. So I need to start with f of my bigger number, so f of 2. That's my f of b, minus f of 1. That's what I know. That is equal to, so if you write this, there's only one thing that can go over here, you guys. The integral from 1 to 2 of f prime. Might be a t, might be a u, might be a v, whatever. This time it's an x. But this is our setup for the first fundamental theorem, for using the first fundamental theorem. Okay? Now plug in what you know. We know that f of 1 is 3. We don't know f of 2. And we know that f prime is 5x to the 4th plus 10x dx. We can evaluate that integral. Okay, this will be x to the 5th times 5 over 5, which is 1, plus x squared times 10 over 2, which is 5. evaluated from 1 to 2. So we're going to have 2 to the 5th plus 5 times 4 minus 1 to the 5th plus 5 times 1. Okay, and then we just bring our 3 over. So 32 plus 20 is 52. 52 minus 6 is 46. So this turns out to be 49. That would be the multiple choice answer. Okay, these can easily be free response questions or a part of a question. Here's what they would need to see. They need to see your setup. They've got to see it. Okay, set up your first fundamental theorem. That's worth a point. Okay. Then they need to see the antiderivative. They're going to be looking for that antiderivative. That's going to be worth another point. And then usually your answer is worth the last point. And if it's free response, remember that you can save stop. Okay? All right. Next example. And this one we're going to use our calculator on just to speed things up. Okay, so I'm going to put calculator on this one. If f prime of x is, and since we got a calculator in our hands, I can make this function pretty complicated. Okay, this one's not going to be just terribly complicated, but e to the negative sine x. All right, and f of 5 is 2. So if we're giving that, we want to find, remember, we can find any other function value that we want. This time we're going to be looking for f of 3. Okay. We know f of 2 and we know f prime, so we can find any other function value that we want. All right? Set up the fundamental theorem of calculus. So f of 5 minus f of 3. Remember to put your bigger number first and then your lower number, your x value. Okay? That will equal the integral from 3 to 5 of f prime. This has to be f prime, right? Now we could have gone ahead and put the e to the negative sine x right here, but it has to be f prime there. Now plug in what you know. I know f of 5 is 2. I don't know f of 3. That's what I'm trying to find. And I know f prime is e to the negative sine x. Okay? Now we're solving for f of 3, and then we're going to, I can stick this in my calculator now, but I usually wait until I have f of 3 by itself. So if I move f of 3 to the other side, it would be positive, right? And then I would need to move this integral to this side, and it would be negative. So f of 3 will equal 2 minus that integral. Right? Little algebra. And this can go right in our calculator. So grab your calculator. Let's see, we have 2 minus math 9, 3 to 5, e to the negative sine x, make sure everything is good, dx. And round to 3 decimal places. Always. In this class, always 3 decimal places. All right, at least. If you want to put more, that's fine, but at least 3. So this would be negative 2.008, right? Okay. Might there be some kind of a numerical method error here? Yeah. Do we care? No. We're just going to round to 3 decimal places. We're good to go. All right? Okay. Next up, let me get another sheet of scratch paper here. I'm going to need some room on this one. Okay, next up, I'm going to draw myself a little graph here, so bear with me for just a second. Let's say -2, 1. So that point is -2, 1 right there, okay? And then 1, 2, 3, 4, 5, 6. All right. So this line goes over here to, and this is the line segment, so it goes right over there to 1, all right? And then at 1, from 1 to 5 here, this is a semicircle. I'm going to make this a semicircle, going down, not going up, but going down. This is a semicircle going down. And if that's true, then this, I'm saying that that is 3, -2, because I made my radius 2, okay? And then over here at 6, so that's 5, 4, 3, 2. And at 6, the point will be 6, 2. So here's another line segment, okay? So a little quick sketch. So this, I'm going to tell you, is the graph of G prime. G prime. This is the graph of a derivative, G prime. And I'm going to tell you that G prime is defined on -2 to 6. Okay? The graph, I would need to tell you, is shown on the left here, and it consists of 2 line segments, and a semicircle. Why do I have to tell you that? I have to tell you that because otherwise you don't really know for sure that this is a straight line. Maybe it's just, you know, some other function that appears to be fairly linear, right? And you don't know for sure that this is a semicircle unless I tell you it is. So these things have to be told to us for us to use some facts about this, okay? It is known that G of 1 is equal to 5. Okay, so let's see already what we have here. We have information about G prime, and we have an initial value of G. So essentially we know G prime, and we know a value of G. We can get any other value of G we want, theoretically, if we know G prime and a point, right? Okay. Part A. Find G of -2. Find G of -2. All right. We know a point. We know the derivative. We can find another point. Set up first fundamental theorem. So first fundamental theorem, 1 is bigger than -2, so I'm going to put G of 1 first. Set up that. And this is equal to the integral from -2 to 1 of G prime. Okay? All right, so what do we know? We know G of 1 is 5. And we don't know the expression for this, but think about what this is. Is that not just the area? We know here's the graph of G prime, and this definite integral is the area from -2 to 1, right? From -2 to 1, we want this area right here. That'll be that definite integral. So that area is above the x-axis, so it's positive. 1/2, it's a triangle, right? So 1/2 base, the base is 3, the height is 1. So that is the area, that is that integral. So now again, G of -2, will be 5 minus this integral. So 5 minus 3/2. That's 1.5. 5 minus 1.5 is 3.5. Okay, but I would say stop right here for this problem. Okay, part B. Find g of 5. G of 5. Okay, well, g of 5, we're going to set it up similar to what we did here, except this time 5 is bigger than 1, so we're going to put g of 5 first. So g of 5 minus g of 1 is the integral from 1 to 5 of g prime dx, right? We know what g of 1 is. G of 1 is 5. And now we have the integral from 1 to 5 of g prime. That's the area from 1 to 5. So now we have this area, this piece. It is entirely below the x-axis. So the integral will be the negative of this area, right? So this will be a negative, and this is where we had to note this was a semicircle, negative 1/2 pi r squared, where r is 2. Like that. So g of 5 will be 5 minus 2 pi. Okay? Part C. Find g of 6. Well, this one we're going to set up just like we did g of 5. So g of 6 minus, all right, now we have a choice. We have a choice. We can use the given point, g of 1, or we can use one of the other 2 points that we just found. I wouldn't want to use g of -2 because that's way over here. I'd like to use something closer to 6 though. Why don't I use g of 5? Because that's really close to 6. So my integral will just be a little area. So I'm going to use g of 5 here, but we could have still used the g of 1. That would have been fine. And this is going to equal the integral from 5 to 6 of g prime. Okay? So g of 6 minus 5 will be this integral from 5 to 6, so the area from 5 to 6, there's another triangle, 1/2 1 times 2. 1/2 1 times 2. And it is above the x-axis. This part of the function is above the x-axis, so the integral is the positive of that area. Okay, so g of 6, oh goodness, I just made a mistake here. G of 5 is not 5. G of 5 was 5 minus 2 pi, right? So g of 6 will be 5 minus 2 pi plus 1. So g of 6 is 6 minus 2 pi. Okay? All right, part D. Find the value or values of x at which g has a relative, let's do a maximum. And we want to justify our answer. Okay, we want g to have a relative maximum. Think about what that means. Go back to our function analysis section, back last unit before we did optimization and everything. G has a relative max. Here's my thought process. G has a relative max when G prime goes positive to negative, right? First fundamental theorem. This was the first derivative test. Okay, G has a relative max when G prime goes from positive to negative, right? So we have the graph of G prime here. Tell me, where does G prime go from positive to negative? Now G prime here, remember, this is the graph of y equals G prime. So y is what we're looking at here. Where does y go from positive to negative? Well, y G prime is positive here, and then G prime is negative here, and then G prime is positive here. I'm not talking about the slope. No slopes here. This is the graph of G prime. So the actual G prime value. G prime of 1 here is 0. G prime of 2 is right here. G prime of 3 is negative 2, right? We have lots of G prime values. Where does G prime go from positive to negative? Right here at x equals 1. So I will write G has a relative, and I can abbreviate relative max at x equals 1, since G prime goes from positive to negative there. That would be my answer with justification. Okay? There's no other value of x where G prime goes from positive to negative. Over here, G prime goes from negative to positive, so that would be a relative minimum. X equals 5 would give us our relative minimum of G. Okay? All right, part E. Got lots of parts to this problem. Find the value or values of x at which G has a point of inflection. And again, we're going to justify. Okay? Point of inflection. So first do your thought process. Point of inflection. Point of inflection of G is when G double prime changes signs. Hopefully you remember that from our function analysis unit. G has a point of inflection when G double prime changes signs. Well, we have the graph of G prime, so what do we do to visualize G double prime? What is G double prime? And we need to say what that is. What is G double prime? G double prime is the slope of G prime, is it not? That's what a second derivative is. It's the slope of the first derivative. So G double prime is the slope of G prime. We need to say this because otherwise in this problem we don't know what G double prime is. Okay? So say that. Alright. So we want the slope of G prime to change signs. So up here, where does the slope of G prime change signs? Okay? The slope of G prime here is negative. It's going down. The slope here is negative. The slope here is also negative. So the slope does not change signs here at x equals 1. The slope changes, it just doesn't change signs. It goes from negative to negative. What about the slope right here? Here the slope is negative. Here the slope is positive. So right here, the slope changes signs. So this will be a point of, this x value will be a point of inflection for G, the graph of G. Here the slope is positive, here the slope is positive. So x equals 5 is not a point of inflection of the graph of G. So down here, G has a point of inflection, POI, at x equals 3. That was that x value there. X equals 3. since G prime changes signs there. That would be my answer. If I say this. If I didn't say this, I'd have to put it down here. Since the slope of G prime changes signs there. Okay? That would be another way to write that answer. All right, last piece. Find the absolute maximum. I think I spelled it wrong. Anyway, maximum, how about max? Value of G and the absolute minimum value of G. Justify your answers. Okay? Well, anytime I'm looking for an absolute max or an absolute min, or both, I set up a closed interval test. So whenever you see, set up a closed interval test. So closed interval test. X is my independent variable. What am I finding the min and max of? G. So G goes here. Whatever you're finding the max or min of goes there. If you want to write G of X, that's fine. Just G, that's fine. They mean the exact same thing, so it doesn't matter. Okay? We start with our closed interval. So what are our boundaries? Our boundaries are -2 and 6, right? So we're going to start with those. -2 and 6. I always start with our bounds. Okay? Now we're going to put in anything that makes the derivative of this 0 or undefined. So those are the critical numbers. So G prime equals 0 or G prime undefined, right? That's what goes here. So G prime equals 0. G prime equals 0. This is the graph of G prime, right? What value of X makes G prime 0? Just those two. X equals 1 and X equals 5. That's what makes G prime 0. And G prime is never undefined. So just 1 and 5 need to go on here. Oops, 1 and 5. Okay? Now we need to find the G value at each of those. What did we do in parts A through C? We found some G values, didn't we? Let's see if we found the ones that we need. Did we find G of -2? We sure did. G of -2 was found in part A, and that was 3.5. Did we find G of 6? We sure did. G of 6 was 6 minus 2 pi. Did we find G of 1? We didn't find G of 1, but we were given G of 1, and G of 1 is 5. And did we find G of 5? Yeah, we did up here, 5 minus 2 pi. If we hadn't found those, then we would have to go off to the side and find those using the same process, the fundamental theorem, that we did for these, okay? So oftentimes in part A or B, you'll find some values that you'll end up using later in these problems. So since we found all these, all we have to do is compare them, find the biggest G value and the smallest G value, right? Well, 2 pi is going to be about 6.28, right? Do you agree? So this will definitely be the maximum G value, and the minimum G value would be the 5 minus 2 pi. That's the smallest. So that's what we're going to write. So G has an absolute maximum value of 5. They didn't ask for the X value, so I don't have to give it to them, but if you want to, you could say at X equals 1, but you don't have to. All they want to know is the value of G, so 5. G has an absolute minimum value of 5 minus 2 pi. If you want to say by closed interval test, you can, but it's unnecessary because I can look right here and see your closed interval test. So it's like we're saying it twice. Okay? You're saying closed interval test, oh, by closed interval test, you don't have to do it both. So you don't have to say this at the end. But if you want to, you can. All right, big unit. I know this was a long one, but this was not big unit. It is a big unit, but this was a big section for us. So be sure to practice, practice, practice.